Ignition sequence start. All engines are running.
We have taken tremendous steps.
We choose to go to the moon before this decade is out.
We have achieved the earth-shaking, the breathtaking, the groundbreaking,
One small step for man.
and left a mark in the heavens. Our successes build one upon another and amplify what is possible.
The dawn of Orion.
It's time we take the next great leap. We're building the next chapter of American exploration, returning to the moon to stay, so we can go beyond to Mars, to expand what's possible and further our understanding. The architecture for these missions is already taking shape. We will go with new systems, bold designs, and a sustainable mission. You can hear it, taste it, touch it. We are going. We are training, testing, pressing our pioneering spirit into every component, defining our resolve with every line of code, and securing our success with every welcomed partnership. This is not hypothetical. This is not about flags and footprints. This is about sustainable science and feeding forward the advance of the human spirit. Because we are the pioneers, the star sailors, the thinkers, the visionaries, the doers. And because we stand on the shoulders of giants to go farther than humanity has ever been, we will add our names to the rolls of the greatest adventurers in history. Every day, every mission, we advance this call. We are NASA. And after 60 years, we're just getting started.
We're going to the moon. This time we're going to stay. We're going to the moon as a proving ground for learning how to live and thrive on another planetary body in preparation for future missions to Mars. NASA Administrator Jim Bridenstine uses one word repeatedly when describing how the Artemis program differs from the Apollo program.
The President's first space policy directive says to go to the moon, go sustainably, and have the United States of America lead a coalition of nations for a sustainable return to the moon.
By 2028, we need sustainability. We're going to the moon, we're going sustainably, we're moving fast.
Sustainable. We also hear or see this or similar words in media postings from space entrepreneurs and international space agencies. Sustainable, reusable, resources. What does all this mean? Before I answer that, let's talk about what it doesn't mean. So far, in our 50-year history of sending humans beyond Earth orbit, we have brought everything we need for the trip from home. And the bulkiest and heaviest thing we need is the rocket propellant that gets us off Earth and safely back. When the Saturn V was sitting on the launch pad, we had big, powerful rocket engines at the bottom and a tiny human space capsule and lunar module at the top. In between is mostly propellant, oxygen and kerosene to get us off Earth, oxygen and hydrogen to push them to the moon, and storable propellants to get down to the lunar surface, back up to orbit, and back home. And while the propellants for the return trip seem small compared to the other stages, it can have a huge impact on the entire vehicle. Think of what happens to the gas mileage in the family minivan on a road trip when we start climbing the mountains. Or worse, when we start climbing the mountains carrying precious vacation gear. Imagine what would happen if the family minivan had to pull a tanker of gas over those mountains in order to refuel for the trip home. As amusing as this image is, because we all realize how unsustainable this method of vacationing would be, this is exactly how we have explored space until now. So how are we going to change this paradigm? We are going to build a gas station on the moon for the astronauts to refuel their vehicle for the trip home. Of course, gas stations only dispense the gas, so we will also need the equipment to gather the raw resources and a refinery to process those resources into rocket propellant. We call this in situ resource utilization, or ISRU for short. Our ancestors called it living off the land. We estimate that we will need approximately 12 tons of oxygen and hydrogen propellant to refuel the lander, get it back up to lunar orbit so we can use it again on the next trip. If we can make that 12 tons on the lunar surface, we wouldn't need to bring it from Earth. While this sounds like a huge savings on its own, because lunar ascent is the last phase of the mission, any savings are like compounded interest, and that 12 tons needed at the end of our trip can add up to much larger savings. In the previous talk, you heard about some of the different parts of the trip to the moon. Let's follow that trip backwards, assuming we make just 1 kilogram of propellant on the lunar surface. In order to land that 1 kilogram from low lunar orbit, we need another 1 kilogram of propellant in tanks, which we also don't need to bring from Earth when making the 1 kilogram on the surface. Our savings are at 2 kilograms. Continuing backwards, we would need another ½ kilogram to get that 2 kilograms from Gateway down to low lunar orbit. So now we have saved 2.5 kilograms. And even with the very efficient slow road trip that is planned to get the uncrewed elements out to Gateway, we would still need more than 6 kilograms of propellant to get that 2.5 kilograms from low Earth orbit up to Gateway. Add it all together, that 1 kilogram we made on the lunar surface has reduced our mass in low Earth orbit by almost 9 kilograms, which means the ability to make 12 tons on the lunar surface can reduce our mass in low Earth orbit by over 100 tons. Also, because we can now reuse the lander, we realize an additional 18-ton savings in low Earth orbit because of all the propellant we don't need to push a new lander out to Gateway on every trip. Altogether, production of propellant to enable a reusable lander could result in 120 tons less at the start of our trip, a substantial reduction from the old way of exploring space. This saves significant launch costs and brings the vision of sustained presence on the lunar surface within our grasp. So let's talk now about some of the technology needed to make ISRU a reality. NASA plans to land near the South Pole, where orbital missions such as Clementine and the Lunar Reconnaissance Orbiter detected water signatures in and near the permanently shadowed regions. And the plume created when the LCROSS spacecraft was purposely crashed into Cabeus crater contained hydrogen components equivalent to 5% water by weight. This data combined has painted a picture of significant water resources, shown here in blue, that can be harvested for life-sustaining water and air for the astronauts, as well as the tons of propellant for the trip home. The first step is to dig up the icy regolith and deliver it to a processing plant. But Newton's third law of motion says that for every action there is an equal and opposite reaction, and the 1/6 gravity on the moon makes it difficult to find the reaction force necessary for digging and driving. So we are working on new ways of digging in compacted granular regolith and in hard materials, where we may take many small scoops instead of big scoops, push sideways against the wheels of the excavator instead of in line with them, or possibly dig at both ends to provide the reaction force. We are working on lightweight compliant wheels made of wires that remember their original shape to provide traction for our excavators. And we are designing mobility platforms with easily replaceable components for prolonged life when we are so far away from our favorite mechanic. Once we have gathered the resource, we will bake it to extract the water, possibly in something similar to a terrestrial soil dryer. Except on Earth, they are interested in the dry dirt, and on the Moon and Mars, we are interested in the water that comes out. So while all of this sounds simple enough, kind of, there are still many challenges to getting to this exciting natural resource and extracting the water for use. First, the water is in permanently shadowed regions, which are surrounded by sunlight, but remain in permanent shadow because they are lower than the surrounding terrain. Terrain maps of the area say that the path into these regions can be long and steep, with most slopes greater than 15 degrees, shown here in green, presenting significant challenges if we want to continually drive in to gather the resource and drive back out to deliver it to the processing plant. An alternative is to do more processing at the excavation site, baking the water out on a hot plate as we dig it up. Of course, this is also not as easy as it sounds, as we have discovered that the dirt flows over the plate much more quickly in a vacuum than in our initial open air tests, and some of the simulants fall out of the scoop more easily than others, leaving big questions about how any of this will work in the real lunar environment. To avoid having to dig up the dirt altogether, we may take inspiration from the workings of a terrestrial Zamboni and create a lunar Zamboni that heats the dirt with microwaves and collects the evolving water as it rows through the shadows. Extracting the water inside the region and storing it in a tanker means fewer trips outside of the region, but more power inside, where that same lack of sunlight that's good for preserving the ice is bad when wanting to use solar energy. Therefore, processing inside the shadowed regions will likely require some sort of beamed energy or nuclear power, another technology being developed here at the NASA Glenn Research Center. In order to move toward our sustainability goal faster, we may start by processing the regolith outside the shadowed regions, where we still have plenty of sunlight for solar energy. The lunar regolith contains over 40% oxygen, bound up in a mix of minerals comprised of metal oxides, such as iron oxide and silicon oxide. By processing this regolith at high temperatures and adding in hydrogen, we can break the iron oxide bonds and extract the oxygen in the form of water. By going to even higher temperatures and introducing carbon in the form of methane gas, more of the metal oxide bonds can be broken to extract the oxygen. While production of oxygen alone from the regolith outside the shadowed regions does not get us all the way to our sustainability goals, 10 of that 12 tons of propellant I said we needed for the trip home is oxygen, so it is a good start. After establishing a foothold on the edge of the country, our pioneer ancestors began pushing westward. We can imagine, because we're a bunch of engineers, we actually did the math, what would have happened if their covered wagons filled with the possessions and tools needed to survive in the wilderness instead needed to carry the food, water, and air for the mules pulling the wagon. Assuming 6 mules can pull a 2,000-pound wagon 25 miles a day, and those same 6 mules require 85 pounds a day of food, water, and air, then our ancestors never would have made the Appalachian Mountains. There are many more parts we are working on to complete our combination mine, refinery, and gas station for the Moon and Mars. When we are done, we will have discovered, or perhaps rediscovered, a new and better way of exploring beyond the bounds of Earth. Thank you.